So today's topic we're going to discuss has to do with memory hierarchy. What we want to discuss is the two basic, really big areas where there are performance detriments have to do with branching and memory. And then everything else is where we can kind of get some speeds. But those ones are ones that you look at and they're just glaring problems that go on. Memory has the biggest single one that's out there because of the difference between the access time for memory and the access time for a CPU. A CPU, you're going at 3 gigahertz, so you're talking 300 and some odd change picoseconds at a stage in order to meet that clock speed. Whereas your access time for RAM is going to be somewhere around 50 milliseconds or more. So we go off there. So let me just, to make sure we've got on the same page where everybody's at. Does everybody remember how the difference between SRAM, DRAM, first cut? Awesome. So when we go into it, the levels of the memory hierarchy. When we go into taking a look at those, does everybody remember the levels of memory hierarchy? If we were to build we usually do this as a triangle. And there's more that goes down. If I were to put up this one, can anybody tell me what's the top one?
Cache or SRAM?
It's registers.
Okay.
I've seen this recently.
Yeah. So under is, that's RAM or main memory, whatever you want to call it as it goes. What's below RAM? Yeah, so I think we almost need to kind of put another one in here. We always draw it that way, but there really properly should, I think, be one more layer in here. What should we really put there? Yeah, flash or solid state drives. All right. What's below hard disk drives?
Tape.
Yeah, tape is definitely below there. So you can put, your tape, your opticals, going down as it goes. Your network access, if you've got a distributed memory system that goes on, all of those take more time to access. And it's basically it's on how much time does it take, what's the latency for access. So these ones and above, this is all SRAM technology. This is DRAM. That's going in. And now you get into areas where you're dealing with flash. And, this is magnetic platters, magnetic media as it goes on. So on and so forth as it goes down. As you go up, you're increasing in speed, which means lower latency as you're going in. But you're also increasing cost. You're also increasing your power per byte and so on and so forth as you're going in. So that's where the trade-off is. I mean, if there was no power constraints, heat constraints, cost constraints, size constraints, you'd build everything out of that. Right? But since there are, we have to go to other stuff. Now, some of the new technologies are coming in are going to start splitting some of these up. That's going in. So there are some really neat ones coming out, up until a couple years ago, solid state drives were small enough that they weren't a major player in the field, but you're getting more and more systems that are using them, and they're significantly faster than hard disk drives. The performance of RAM doesn't really change that much. It's usually anywhere from 50 nanoseconds up to 120 nanoseconds. The big range, most of it's actually really 50 to 60 on an access, but it's a double access when you have to do a read. Right? Why? You got that yesterday, so.
You have to write it back.
Yeah. When you read it out, you discharge the capacitor, you have to write it back. So it takes it out twice as long. That doesn't mean the CPU has to wait that long, though. So part of the reason when you look at this hierarchy, you should be thinking about what goes on. When you're accessing, the only time it really matters on the speeds, as far as we're concerned with, is how much time it's going to take to the CPU. What type of a drag is it making on the processor? Well, if you're trying to access something and you're reading it, I really should only have to pay the first access time. And then I make the system itself update its own memory. Right? Why should I have to wait for that? That's a write back. Now that means it'll be less accessible while that's going on. Right? Now, that could potentially create a problem, so the easiest way to do this is, at the level of a RAM, we put another cache level on top of the RAM, so on those RAM chips. And what you do is when you're going to access something, you move a block off, right, into an SRAM cache in your memory area, and then I refresh memory from that, so I can just kind of do it blocks at a time. And it's called dynamic memory anyway because those capacitors are discharging, so you have to kind of cycle through it regularly anyway. So as you're doing it, you know, you're not completely inaccessible when that time's out if you do it. How about cache? Since we started kind of covering those, we mentioned we really kind of have a little cache, often level 3 cache, that goes onto the RAM that's handling that cycling on and off. Right? Do we do anything similar like that on hard disk drives?
Yes.
Yes. Right? On those, in order to send out to the network, hard disk drives are really slow and you got a rotating platter, so you've got a latency, both in two senses. Right? You've got a magnetic head that's reading this, that's going on, and it's got to move in and out as it's going. So you've got a latency moving radially, but you've also got it spinning. And so if your data is over here and it's got to rotate around in order to get it, you know, you've got to wait for the data to come around. So when it happens, you often read them. That's why it's better to have your disk defragmented, because then everything's close together. And if you think about the closer I get to the center of the disk and the tighter packed everything is, the less moves I have to make anyway. So if you spread your stuff all over and it's in different locations, you're going to have to keep moving that head to different locations. Does that make sense? So what you'll often do with that one is you'll put a little section of RAM. And when you're accessing some areas, you'll offload into RAM, but it's functioning like a cache. It's going in. Now, most solid-state drives are actually fairly fast, so you're not having to pay as much areas on them. I could theoretically put some cache, but solid-state drives are getting to RAM speeds that's going on. So, you know, usually there may be an order of magnitude slower now for some of them, but it's pretty close. Oh, it's not a huge penalty that's being paid on those. Nowhere near that's on this. When you're going to here, the rotational latencies, when you think about it, going in or out or rotating around, this is usually summarized by the access time. And those ones are typically somewhere between, you know, 3 to 8 millisecond range. Right? So now if you put those in our terms, you know, you're 20 million operations or so to kind of the middle of that range difference when it goes on. That's really pretty painful when it's going in. So this is like really, really harsh. That's why we don't like disk paging. So we always use this idea. Now, here's the big takeaway from all of them. When we're dealing with this hierarchy, I'm not only going up here getting this, I'm also getting smaller because of those. So if you consider, you know, a RAM, a decent computer now has maybe 8 or 16 gigabytes of RAM. Right? So this is, say, let's say I've got a 16 gigabytes of RAM. About how big's my cache going to be?
Not nearly that big.
Yeah, so I'm talking somewhere in the megabytes range
Yeah.
that's going in. Maybe, you know, 1, 2 megabytes, something like that. Now think about if I'm trying to hit, that's just in RAM. I mean, I'm talking when I go to a hard drive, I'm in the terabytes range. Right? So it's not unusual to have something like 2 TB, right? Or more. So if I'm dealing with something like this, how can I expect that when I'm trying to access some file or something that's on here, that the data I really want is likely here, or here even, when trying to get to something orders of magnitude different. If I was talking a pure random process, think about what the probability would be. What would be the probability if it was totally random where the axis is? That this, you know, something I want to find here was here,
Yeah, pretty small.
right?
8,000 or something.
You know, I mean, if it was completely uniform across this, You'd be talking, just on this one, one in around, 8K. Right? And I say K rather than 1,000 because to us it's, 2 to the 10th, which is 1024, so it's not exactly 1,000. It's a little bit over. But, so we'd be talking, somewhere around a 1 in 10,000 chance. That's pretty unlikely that it would ever benefit me. And yet, our hit rates on the levels of cash that are in there tend to be somewhere in the range of, 97, 98%. So well beyond what you would expect for it. So why am I so, unparalleledly lucky in getting these? Yeah, that's the basic rule of real estate is location, 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 right? So the basic rule, we're dealing with real estate, it's memory, right? It's an area that goes on. So ours is locality, locality, locality. Two types. They are, anybody remember?
Spatial.
Awesome.
Temporal.
Spatial and temporal. Great, right? These are the two, whenever you're looking, what you want to do with any memory hierarchy issue that's going on. You want to look at them, you want to identify them as one of these, and that gives you an idea of how to solve it. Okay? So spatial locality is?
Something that's been accessed is more likely for something next to it to be accessed.
Exactly. And the basic reason that's the case is think of how you program. If you were going in and writing a program in C or something like that, you might declare int x, y, z, right? And then you do something with it. So since they're declared right next to each other, it's going to put them right next to each other in memory locations. Since they're right next to each other, if I start accessing x, it's likely you're going to do something with y and z. So what do we do to take advantage? What's the basic one to take advantage of spatial locality?
Grab the blocks, so we go over.
Do a block of memory at a time. Right? So when we access, if you ask for x, I'm actually not going to grab x, I'm going to grab an entire block. Usually it's anywhere from 4 to 16 variables at a time. And I'll load that whole thing in. Now why is, that thing happens pretty much universally. Why is that helpful? I mean, locality obviously, but if it took me as long to grab all those, I would be paying a lot of penalty. So there's some advantages I have to be taking care of to make that efficient. And if you don't take care of those things, it becomes really inefficient actually. So it's a potential to get an advantage, but what do we do to make that advantage really happen?
First reading.
Okay, so think of it this way. I've got these sequential blocks and I'm going to get this blocks of memory that's going in. Imagine x was located here. Right? So if I had to load them, and I loaded them in order as they're coming across, sending one variable across the line every single time, your CPU would have to wait several times before x came up. And that's what it wants to see. That would make the CPU wait longer to get its first variable, to save you time later. But then you've now canceled your advantage out. So what we usually do is give you what's called the first requested byte, or requested first. There's a lot of little nicknames or monikers for it. But the idea is when you ask for this, I'm going to send you the whole block that's in here, or the whole block of the addresses, but I'm going to send you this one first. So that lowers the latency to get it, and then I'm going to fill in the other ones as is needed. Now it doesn't cost you anything extra. Now, that's cool, but that's only one part of it. If each one of these took 50 nanoseconds to access, that's going on, it could still be quite expensive because now I've got my memory out of commission for a while. So what do I do to prevent that one from happening? So requested first saves me on the latency to the CPU. What saves me on the total access time? Bursts. Yeah. So the whole idea behind burst goes like this. It's really slow to access RAM. But it's actually not as slow if you're going to access a bunch of them. because I can, first off, do this in parallel. When you get an address that's going on, imagine that, leave this anymore. Your basic access cell is I've got an address line here, I've got a data I/O line here, and I got my transistor. I go into a capacitor and I assert the address line, transistor opens, you can read or write to the capacitor. That's the basic setup. So imagine every time I have an intersection, I've got this. Okay? And I should really put my connect dots. What's going on? All right, when we deal with this, I can put a whole bunch of data I/O lines. That's where we're going in, and a whole bunch of address lines. Which means when you're accessing, I don't just give you one at a time, I can access a whole bunch of these. Now, this type of a setup, right, where I have all my DIOs here, and I got my address lines, this is on one individual RAM chip, so I can get a bunch out. But why can't I do a whole bunch of chips? If you ever look at them, you actually have a bunch that are available. So I get even more information. So I can start sending you big blocks at a time, and if I interleave the writes, so I put the first group here, the second group here, the next one there, you can access them all in parallel. And it's spread across. So it's the same latency to access any of these, but I'm now sending out a huge increase in bandwidth that's going on, which means a larger chunk of stuff. Now, some of these systems only let you access one bit at a time. Some of them allow you to access more. Some of them are reconfigurable. There's options on how they go on. We often treat them, at least for the initial talk, about one bit, particularly on the earlier ones, because you have different ways you can configure them as they're going. But we also have a second advantage. In addition to this type of thing where I've got addresses in here, when you're accessing sequential addresses that go on, you're following a pattern of how you're moving down. Now what normally occurs is I've got to send across, here's the address I want, it's got to load it into a buffer for these. You read them out, goes into it, goes amplified, goes into a buffer, and then gets sent back out to you. But that would mean the next address, I'd have to send another address to it and keep on going. So the question is, how can I build this so I can do blocks at a time? Does that make sense as a goal? So how can I do that?
Put in a counter.
Yeah, exactly. And if you're dealing with addressing that's like 32 bits or more that's going on to access this, it's kind of tedious to keep incrementing a 32-bit thing. But are you really going through all 32 bits, or are you only dealing with some of them?
Likely just.
Yeah, probably just a few of them, right? If I'm doing byte addressable, that's 4 per particular int that's going on. Maybe I'm dealing with up to 16 of them. So maybe I'm doing 64 bytes at a time. Right? So 64, so I'm going 0 to 63. That's as tough as it gets. How far could the carry bit ripple? Because we're all familiar with ripple carry adders, right? How far could that go? The question kind of is, if I've got a 32-bit counter, can I just run that into an adder that's adding 1 each time, feed around, you know, how many bits can change at a time?
If you do the full 32-bit edition?
Yeah.
Oh, well.
Because you have to consider that possibility, right?
Well, that's a pretty big adder. I mean, it could ripple almost all the way across.
Is it possible for the setup I've drawn here to ripple all the way across?
4 bits.
It could ripple the whole way. I mean, I could add 1 to something. I mean, if you had 1, 1, 1, 1, 1, 1, 1, right? If you had the largest int and I had 1 to it, it could ripple all the way across. So, in theory, in general, I might have to deal with that. I now assert to you, however, that it will never ripple more than across 6. Why?
6 bits to address 64.
Yeah.
And think, what's the first address?
Yeah, it's started with zeros.
It started with all zeros. So since it started with all zeros and you're doing a block, right, you keep adding 1, 1, 1, and you're gonna stop before that one ripple that carries out of your 0 to 63. So really what you're doing is counting 0 to 63 with something else appended on the front. So we can split it. We've got however big your block is, whatever bits it takes to address that block, and everything else. That make sense? So that makes it a lot easier on me, and I can actually even split it even more so. I mean, let's say for instance I split this into 10 bits, which is going to be dealing with which particular byte you're dealing with at that instant. And I could go to my next group of 10, that's going to be which little block in memory that's going in, right? And I've got extra bits in here where that can deal with memory partitions and all kinds of other stuff. This kind of gets into how virtual memory is breaking stuff up. But I really only have to deal with a small subset of them because these other numbers aren't changing. You're not moving out of your memory partition. So as long as I correctly align my stuff, which, I mean, I'm in charge of my compilers, so I should do that, I can be guaranteed a simpler setup. So what we do then, or coming into them, is we actually set them up also 2D in that direction, where we have the address for the rows and the columns. And I only need, so we have a little memory one off here, and I only need to run this one through the adder. And then of course I have a mux select here in memory. So when you load them, I load in the row address. Once I've loaded that one in, it's not going to change anymore. So that's fixed. I add this one in and it just walks through sequentially, just sending them out. So that means every time I'm accessing it, I'm no longer having to do any data transfers coming in. So that reduces my overhead. And then I can do it as fast as I can read them out internally on the chip. That speeds up accessing a block. So I can then also be hiding some things. As I'm offloading, think just like your pipeline. As you're offloading these into the cache, I can have a separate unit preparing and packaging it to send out. Right? So all my network communication, everything else can be done in parallel to this to hide some of that latency. So if we kind of break our timing down as we're going into it, you kind of have to pay that time for the first access. And then the second, as you're going on and you're doing the stuff, whatever it takes to do the transfer, right? Accessing the next one doesn't take this full amount. So I can get that one here for whatever the subsequent access time is. Right? So if you consider time is increasing this way, and this is just things I'm doing in parallel tasks, right? First one that comes out, second, right? And then its transfer. And while it's doing that, I can be, doing my subsequent access thing. That one doesn't change. And so every transfer after it looks really small addition. Does that make sense? So that's why burst mode works. How does, under this setup like this, how does transmit the one you want first work? Requested byte first.
You could start the column where you actually want it, and then wrap around back.
Exactly correct, it wraps. So I don't actually even have to start at 0. I can start any number you want, and since it's going to wrap around, who cares? It just means you'll get the bytes before it will come really late, but you don't care about them. Right? So if you think about those as it's going in, it makes perfect sense. It's really easy. It takes no extra hardware. I can send them in whatever order. I just have to make sure the other system loads them in the correct order. So those are very easy additions that now allow me to handle those. So what I want you to do is when you're thinking about each one of these different areas, ask yourself the question, how could I build it? Because that's what it kind of comes down to. So this one would be pretty easy. I've got this kind of two-dimensional array that's coming in. And when I want to pull the bytes out, I can just panel the DIO, the IO stuff, up to another plane. This is on one plane where you're accessing the stuff. I run the bits up to the next level plane, right, that's going in. I can tile a bunch of these across to get a whole bunch of them in it. Right, so if you consider one bit right here as an area, I can tile a whole bunch of them to get multiple bits. And I can just run their data out to a higher level and then amplify. You put an amplifier into the cache and you're done. So that's a pretty straightforward build, I think, as we're going in. Does that make sense? All right. So this is why we can do those type of block transfers, the spatial locality part. What's temporal locality?
Something that's been accessed or something that's been more frequently accessed is gonna keep being frequently accessed.
Okay.
Recently.
Yes.
Yeah, recently.
So this one affects how you keep stuff in cache, right? Because it's basically saying if you're using something a whole bunch, you're probably gonna use it again. Right? If I'm calculating my X, Y, Z, and I use X, it's a higher likelihood I'm gonna use X now than 1,000 cycles from now. If I haven't used X in 1,000 cycles, I'm probably done using it. What in our programming enforces that type of a thing?
Local variables.
Yeah, local variables. This is why the ideas of subroutines and functions, because we use those, you tend to get really good locality in time. Because you leave a function, you can't access that memory anymore. So therefore, there's no reason to keep it in cache anytime I hit those. So I've got nice little defined boundaries. So there is an advantage to a certain amount of functional areas. You make them too big, you're going to lose some of this. It kind of fuzzifies things. Now it'll save you on branching. So it's a trade-off. Now you got to look at where is the efficiency on those spots as you're going through. Right? So how can I improve temporal locality inside my system?
Well, this is more at the cache level.
You know, in some sense, they're all, because that was level
Yeah.
3 cache,
Yeah,
but it
if you
affected
want
what
to
the space,
right
there's
now,
other
the
spatial
same
locality ones
ways.
too. This one's
Yeah.
the easiest one to get from spatial. And we'll deal with some others that's going on, but I want you to be thinking build. What could I do, what's the biggest thing that we do to handle temporal locality?
Could you use some sort of queue data structure that would have, I guess, the address of something that's been accessed and you access something else that puts it on the end of the queue? And
Okay,
if it's not in
so,
the queue, then it shouldn't be.
so now I want to start trying to say, how do I keep things? I've only got so many locations, right? I mean, when you're going into them, you're level 2 cache, I maybe have a few megs. When you get down to level 1 cache, you're talking tens of Ks, maybe hundreds of Ks that's going in. So really small amounts of space. The likelihood of me running out of space is pretty high. So if I'm going in and dropping a variable in and my cache is already full, who do I kick out? So temporal locality is the one. Now, we've got some candidates of what we can do. So Oldest was suggested, what else could we do?
Least used. Random.
Actually.
So we had somebody who's red, right?
Yeah.
But we'll get a thing that goes off. I'm gonna add, it's not just least used, because there's actually a difference between least used and least recently used. Right? This talks about how many times total you have used it. This talks about the time period from when you last accessed it to now. This was whoever was loaded first. Right? This one just means Russian roulette. Okay, and that's what you're doing, right? I mean, just boom, right? And you just walk out, who's gonna get shot? Of these two, which ones perform best?
Random does pretty well.
Random does really darn well, actually, for a decent sized cache. The smaller your cache, the worse it does. Why would you expect random to work well?
Because your code is not necessarily that organized.
You know, that's one way that gives in. The other one is law of large numbers. as your cache gets bigger and bigger, it's gonna move towards the sample area that's going in, according to its distribution, but we know the distribution. So it's not a uniform distribution, but I can take advantage of things, but once it's in here, it's much better of what's inside as opposed to the whole thing down. Right? So random does pretty well. Of that, there's one that can beat it, but it's often not worthwhile. Yeah, this is theoretically the best you can do without knowing the future. Okay? If you know the future, you can do better. Can I know the future?
Your compiling might.
My compiler can know the future. How can my compiler know the future?
Sees all your code.
It sees all the code.
Yeah.
So, when you think about it in that sense, it sees the entire time frame. Now, it doesn't know what the current variables are, and there is some randomness within your code. We often think of code as deterministic, but it's not. Right? Because a lot of your code depends on user input. Because huge amounts of your code is, you know, if the user does something in a particular instance, your code has to respond to it. That's the whole idea about event-driven code, and a lot of code is event-driven. So it depends on the event sequence.
So is its choice of selection scheme, is that also dynamic? So like, if, for example, if you have a real-time application, would it want to choose least recently used because it knows it has a hard deadline, versus if it's just a regular application, it can just use random?
So if I was dealing with a system that had to operate in real time, I'm probably dealing with an embedded system, and what I would probably do is not put RAM on it.
Okay.
So I would make everything out of this. That's what we call systems on chips and stuff. We just make all your available stuff right out of the fastest things possible, and it's gonna be small anyway, but I can't tolerate a random delay. So therefore what I'll do is I'll just give you everything fast, and you're willing to pay for it because it's not a lot. But we'll make it enough, and then you don't have to worry about that at all. So for those type of systems that's time critical, pay the money, right? If it's not that time critical, then avoid it, because when you're dealing with embedded systems that have to be real time does not mean fast. Real time means that if it doesn't happen by a certain point, you better not do it. Right? Think of like a plane landing or something, right? It's reacting to turbulence. If it's trying to say, oh, I need to adjust, you know, I just got kicked up a little bit, I need to adjust down slightly. If it does it too late and it's already started coming down, and then it goes really more down, you can actually end up, because of that latency, getting more and more overshoots, and it becomes unstable. That's a latency, okay? When you're dealing with it, a function, t, you know, with some delta t added onto it, when you take its Fourier transform, what does that time shift become? It ends up, but it multiplies by, you know, e to your j omega some c that's going on. This, in the complex plane, spirals. It's an exponent, it's circular, it's going on. Since it's spiraling, when you go in and draw that on your axis in the Laplace domain, where is your gain in phase margin? Well, it's how far you are from the -1 point, right? So if you were originally here and I put a spiral, what happened to your gain in phase margin? They just, because you're asking how far away from this is, right? Gain margin, distance, phase margin, right? So it just got shot to hell, didn't it? It's just completely gone. So if you have a delay, any latency lag, it causes your system to become really unstable. That's true with ours also, when it's going on. This is a universal idea. So when it does that, that's why the overshoot and the instability happens. So when it's time critical, this is going to enter into an important equation. I got to knock it out, because I must avoid the spiraling in the frequency domain. So these ones go in as you're going. Now, least recently used means I have to track them all that's going. So I have to find out who has been accessed not so recently. So I have to, if I've got a bank of these, and this is when you get into what we call the associativity. How many different locations can you store it in? And in any particular bank, the addresses you can use interchangeably, it's either 1, 2, 4, or 8. And 8 is rare. that's going on. This number is all I'm tracking of how many of these do I have to track how recently they're used versus each other. Because it's not anybody, it's just the ones that are interchangeable. And so every group will have its own little subset. And like I said, these are by far the more common. Why? The higher the associativity, the better things should be, right? Wouldn't 16 be better than 8?
It's an implementation thing, probably.
It is an implementation thing, but it's also what we call diminishing returns. The benefit you get from going to 8 to 16 is small, but the complexity is huge. So the relative return of going up there is really tiny and therefore not advantageous. The reason why 4 is more common than 8 is, again, when I'm checking those, it's decently more complicated, not horribly, but it's a decent amount, and the returns are really small. I get a really good advantage from 4. Therefore, there's not as much to eke out when I go to 8. So the added complexity is often not worth it. So I might be saving an extra 0.25% by going to 16, but it costs me way more than that. I'd be better off just making more locations. And realize I have to search all those other ones parallel. So I have to build parallel hardware for 16, that's getting really expensive. Right? Does it make sense? Okay, so what's the most common mistype that we have in a system, or what are the common problems that go on? So this kind of gives you an idea where the basics go, and hopefully you can picture in your mind how to build it. Yay? Okay. What's the most common mistypes that are out there?
Like cache miss for.
Yeah, what, I mean, because every time you get errors, our function for calculating these, right, we always come down to it's basically how you're calculating means on anything else that's going on, right? We have whatever our access time is for that particular level, plus the miss rate for that level, times whatever the penalty is. So that's the time for the level. And that penalty is the time for the next level. So you just keep recursively sticking this back in and you get everything. But if you think about this one in a sec, this is just a weighted average. I assert to you it's a weighted average. Right? Now, when I say I assert to you, guess what I'm just asking? I make it as a statement, but there's kind of an implicit thing you should always do.
Prove it.
Right, so you've got two options. Number one, in your head you should immediately say, can I prove it? If you can prove it, you're like, yeah, of course. Right? And if you can't prove it, you should say, you prove it. You call me on it. This lets us kind of go faster as we're going through this stuff, what's going on, but it also prepares you for when you're going out, right? You're going to go out with a graduate degree, master's or PhD, depending on wherever you're at. People are therefore going to expect you to, in some sense, be an expert. So when you're calling there, you're seeing something, you got to be willing to look at something and say, hey, you know, good, not good, that's going in. You know, makes sense, doesn't make sense. People will assert some of the craziest things in the universe. They're not always right when they assert it, even if they've got a lot of credentials behind their name. Right? In some sense, part of being a PhD is coming up with wacky ideas we have to check. Right? If I don't generate wacky ideas, then you don't break out of the norm. So you've got to kind of get into that mode of going on, and there needs to be a little bit of friendly disbelief. Can you prove that? That I make that that's a weighted average?
You'd think that you'd advertise the fastest access time just to show that your memory is faster than others.
Yeah, most people just report that. You're exactly right. That's a marketing trick that goes on, but you're absolutely correct. And I only report the access time for one thing, not a whole bunch of stuff. Yeah. But then we have to come in and say, hey, what can it really do and how can we really make this improve? Right? So can you prove that this is just a weighted average? Everybody's staring at me. That means, no, I can't. So, let's just do it real quick. You know, the trick that's in here, almost every trick in math comes down to multiply by 1 or add 0. Honestly, in almost every proof that's out there. So I'm gonna multiply by 1. But you picked the correct one. There's only 2 options, miss or hit. So the miss rate plus the hit rate is 1. We agree? So I'm now going to separate. So I've got the hit rate times the access plus the miss rate times access plus penalty. That's how likely it is if you find it in cache and what it will cost you when you go into cache, plus how likely it is that you miss it and how long it will take you to get it if you miss it. Therefore, it is a weighted average of the 2 options. Really all we're doing. We're just saying, hey, there's 2 options. How long did one take? How long did the other take? Multiply them by the frequency, add them together. Weighted average. But this one is often, this is not a particularly convenient form to write it in because you got to calculate them. So what we do is we just regroup them. Everybody has to pay that, and those that miss also have to pay that. This form is easier and it's easier to access, so that's why we rewrite it. But I want you to be thinking all you're doing in here is weighted average, because every performance metric we deal with is a weighted average at every level, and I don't care whether it's cache, I don't care if it's branching, whatever else, they're all weighted averages. That's all we do. Right? And it's usually of 2 options. So it's a really simple weighted average. And then we present them as a million different equations. So it's worthless to memorize. Good? Okay. So one of the most common things, when you start looking at them, what could happen when it's going in? Right? Think about the problems that could happen that could cause it. Well, why might I miss it? Well, what if it's not in there? Well, why isn't it in there? Right? So we call this sometimes failure analysis or Ishikawa analysis. There's a couple different ones. Fishbone is another one that goes in. So we just keep asking why. It's sometimes called the 5 whys. There's a bunch of different ones. Right? But why isn't it in cache? Well, maybe I'm just starting up. Right? So that's one. We call those cold misses. Well, what can I do to handle cold misses? Well, in some sense, you can't get rid of them totally. But when you first start up, there's only a few options that could be going on, right? I mean, there's certain things you have to do at the startup. Since I know what those are, I can actually put to prefetch those right at the very beginning. Now, what if my hardware doesn't have a built-in prefetching unit? A command to prefetch. Well, I could just put in a couple load commands for the first starting address. So I could do a cheesy way. Now, that ends up taking some of my registers, so it's a little bit wasteful, but if I don't have the hardware command, I can force it. Now, it would be nice to just say, I'm going to need that, and it just queues it up in the cache as something I have to handle. What else, what other types of reasons might it not be in the cache?
It's been replaced.
Okay, so it could be kicked out. Now, this gets into those areas. If I kick it out, right, there's a chance when I do a replacement, particularly with random, that I might replace something important, right? Even least recently used could replace something important. It could be like a global variable, and I just went through a local cache or something. Right? So it's possible one of these could do it. So what can I do to make sure that thing doesn't just get shoved way down too quickly? Well, what if I give myself a last chance type of thing, right, at my level? Let's say I'm at level 1 cache that's going on, and I've got all my different locations in the block groups. What if I append on the side a little queue that's going on? And when I'm going to get rid of something, I stick it onto the queue, and then that queue is the one that writes them down. We call this a victim buffer. The idea of a victim buffer is this. Now you can just check these few locations. So it gives you a couple last spots to go. On top of it, how critical are writes to the timing of my system? Does it affect my CPU? No. Reads affect my CPU. So if I'm doing some writes down, that means the CPU cannot be doing reads. If I've got a very limited resource, particularly if I go out and there's multiple processors accessing it, each one with their own cache, processor 1, processor 2, so multi-core system, it's going in, then they're all sharing that same access to RAM. So now I got more of them trying to access on this. So if I'm writing, that means this one can't be reading. Since this is low priority, I should stick it to when it's not very busy. Right? Think of like a freeway system. Are our freeways uniformly busy?
No.
No, it's like much busier at rush hour. First thing in the morning when people are getting to work, you know, and then when people are getting home for dinner. That's when you get all the traffic. Well, what if I could take half those cars and distribute them throughout the day and it didn't cause anybody a problem to move them around? Wouldn't that be nice? So we actually used to do this type of things with railways back in the 1800s. To avoid the conflicts with things, we would do shipping late at night. That's why you often still hear trains late at night. That's going on. Because they do that so that when they're moving through metropolitan areas, you're not moving trains through when people are trying to move a lot of cars through. So you reduce the number of areas. That's also why you get more train accidents at night. Same thing for us. We want to distribute them throughout. Well, by making a victim buffer, we can pull those other ones over. It means I can send out things during times when there's less reads. So I'm using my resources better. It evens the load, and it leaves them in here longer, so I can take more advantage if you miss something and handle that temporal locality that you just, we call those collision misses that go on. So we often call these the C's. We try to get everything down to the reason of the problem was some of these misses. So a cold start, right? Kind of like cars starting up in the morning, it's cold. A collision miss that's going on, right? So these are all hitting on to those different areas. So in order to handle that collision misses, I can create a victim buffer, and I can then use this to also handle parallel situations and evening the load. This has an added bonus that goes on. Once I have a victim buffer, I can also handle problems like writes. When the CPU goes to write, if there's nothing in the cache at that address, then it's likely that you're just storing it. Right? So typically, if you're going to be continuing to do stuff, the first time you see it is not when you're writing. Usually you write when you're done with something. So if you never read it and you're writing, how likely are you going to use it? Fairly low likelihood. So we're trying to take advantage of everything we can to pack the small area. So these ones have to do with what we call the creation of locations that goes in. Well, if you've never done it before, we just stick it right in the victim buffer. And at that point, it's guaranteed it'll get down. So the CPU doesn't have to wait, it just keeps right up moving. So that permits the CPU to continue to move past writes. So we often get pretty much no penalty for a write because you just continue past. Make sense? So this one little addition of a victim buffer handles a lot of problems that go on. Basically all writes disappear, as long as you don't overflow the buffer. So how can I make sure you don't overflow the buffer?
Seems like it would have to be partly a consideration of timing.
It is a very big timing issue. And it has a relation to going to networking problems. The same exact problem happens on networks, which has to do with traffic. You ever notice that when one person is checking their cell phone for their email or whatever else, a bunch of other people are too? People get out of class, what's the first thing they want to do? You know, they want to, check, did I get something new? Did my friends ask me to go to lunch, whatever, right? So you're the second, and that's usually a block of people at a time, which means if you look at your network traffic, just like when you look at our network traffic, you get these spikes. When you tend to read a bunch of data, process data, read a bunch of data, process data. So you get these spikes. that are going through. Ideally, the best system would be completely level. You get even utilization and no spikes that's going on. But you're not gonna hit that, so how do I make sure I don't get a spike so big it fills it? Well, I have to, two ways. Number one is I can measure what's currently going on and try to fit a distribution. And then I can set this so it's a little bit bigger or slightly bigger than what I anticipate I would need. The other way is I can mathematically model it and then try to pick one and say, what's my confidence interval that at this particular size, I'm not going to exceed it? Can I guarantee that I can get you enough? No. But if I had a Gaussian process, could I pretty much guarantee? I could give you a really high confidence, but I can't in real life. Why? It's an obvious implication of that.
Real life
It's not Gaussian.
Yeah.
Okay. The problem is that we have all the access things we've seen, whether it's networks or memory, or what we call fat tail distributions. Right? They've got way too much probability out there. Right? So there's a couple different ones. The most common one used for this is what's called a Pareto distribution that's going on. It's a really heavy tail on it. Right? Chi-square is a very heavy tail one. These tend to be with what's called fractal access patterns that goes on. And because it's fractal, it keeps recursing inside, so it gets very high likelihood of a very large distribution. So if you look at these, you'll see kind of that same type of access that you see noise-wise for everything else, but every now and then there's like spikes that are just crazy big, right? And those, it doesn't level out. With a normal Gaussian, you would expect that it would kind of level, that you can zoom out far enough that you just don't see big spikes anymore, except so rare that it's just unlikely to ever happen in a practical time period. That doesn't happen with these distributions. So you cannot ever, ever guarantee you are going to have something big enough. So you just have to say, hey, within a reasonable time frame, it's not. Which means the system has to watch it. If that thing ever locks up so it's full, the CPU now has to stop. Right? Now you have to wait, now you have to clear stuff out to get that going. And so it will occur, usually it's set up that it's fairly infrequent. You know, you're talking millions of cycles between problems, or billions. But it cannot be non-finite.
This is where buffer merging helps too, the right back buffer.
For each of these so there's a lot of different things you can do, and this is where you start going in, hey, how can I make this better? That's going on, right? And the bigger trick that goes into this is, even beyond just this one, now I've got multiple ones that are writing out down to RAM. And this is kind of slow as it's going in. Now, to kind of take advantage of this as it's going really slow here, we also hit one more little interesting area that goes on. It's possible once I get to multiple of these, that when I'm trying to access this, I could have, these could be running the same exact program, and maybe I want to read X. This one could have X, but in addition to having X, it might have modified it. It read it, it wrote to it, but my write might not have made it all the way down yet. Right? Because I'm deliberately saying I'm delaying writes. But what if what you want was delayed? So when you come out to ask for it, you don't get the current version. Could that affect you bad? What do I do to handle that? I'm in deep trouble. This is where you get to the coherence and
Yeah,
consistency.
you need them talking to each other.
Yeah, so this one has what's called a snooping protocol. All of them do. Snooping protocol, think of what it means to snoop, right? To sneak around and look. So even when they're not writing to them, they're always watching. So they're not just always listening up to their CPU, they're also listening down to the next level when that level is merging multiple together. And so now they watch these, and if they see a request for an address they have, they'll send out the answer, and this level's faster than this. So this system is watching, and if it hears, get this, and then this one says, here it is, this one cancels what it was doing and updates to what was just sent. So we call those snooping protocols that go on. And at this level where you share a common bus, a single core thing, it's really efficient. So multi-cores and SMPs and things like that, this is pretty common. We always have at least 3 states on these for what's in memory. This is part of what's going on your address tag that's happening, right? It's either, you know, a value that's valid, that means I've read it, but I haven't modified it. I've got a modified state. I've got I, which means it's, you know, it's not a correct version that's in. So I've got those 3 ones as a base, right? I don't have it, I have it, I have it, and I modified it. Now, this is when you get into where the snooping protocol, how many bits does it take? 2 bits. So I only need a 2-bit little automata to handle this. So this is a small thing, so I can make it crazy fast that's going on. But I have to do it for every block. Because I have to track every single one of my addresses I have to be watching. So I'm going to make a whole ton of these little tiny machines that are ready to respond. And when I see something on here, I toss out to say, hey, anybody got this? So they can now all do it in parallel, so I can do this crazy fast that's going on. But they all watch them, and they're just, each one of them is saying, I have it, I don't have it, it's been modified. If I'm a have it, but I'm about to go to modify. So the book gives you these example protocols that go in, but if you think about them for a second, it's pretty easy. If I don't have it, clearly I don't respond. If I have it in unmodified, I just give it to them, right? And I can stay on. If I have it in unmodified, I have to send it out, again, just because somebody asked for it, so I have to send it out to them. But at that point, this is going to update it, so I'm no longer modified. So I also must move my state, right? So I'm no longer modified. I'm now just, I have it. And there could be multiple people that have it. So then imagine I have it, and I'm about to change it, right? So my system is now about to write again. But that means somebody else could have it. Have I tracked everybody who has it? That gets kind of expensive, doesn't it? So what do I have to do?
Let them know you're changing.
I have to let them know. So I have to send out something on there that says invalidate. So I have to send a message across here on the right. It's got to be a small, lightweight message because I don't want to clog my bus up. That just says, I'm changing this address. So those 3 basic states are the simple ones. Now somebody, you could look at that and say, hey, what if I realize I'm going to keep working on X, other people might want to read it. Maybe what I want to do is just not let them store a copy, then I don't have to send that out. I can say you can use it, but you can't store it in cache. So every time you want it, you have to ask me. Right? We call that exclusive. So just like there's invalid, valid, modified, we could give you an E, exclusive, which means it's mine. I'll let you know what it is, but you can't cache it. You can just take it to your registers and use it. And then if you're going to need to get a new value from it, you're going to have to ask me again. But then I never need to go out and modify it. I'm always the sole source, and I'm definitely faster than Graham, and I don't have to worry about telling everybody when I keep changing things and it's irrelevant. Right? So we've got all these different ones that are in there, right? I've got exclusives, I've got owns, right? So there's different levels that we can handle into these to allow me to speed up and reduce some of the protocol areas. But that's going to depend what the access of your programs are. It will help you under certain types of accesses, which means certain types of programs. And it won't help you and can even hurt you under others. So now you've got to profile what people are going to run on your system. You configure your hardware to how they're going to use it. Make sense? So in each one of these things, if you look, we looked at it and we said, where could it break? Where's the problem? If you come up with a solution, that solution is advantageous in certain areas, not in others. So we've got to see how well does it fit to my users. Not every system has the same exact usage profile. a high-speed HPC server is gonna be a very different usage thing than